Today we are taking a look at characteristics of exponential functions, and we are looking at very special types of exponential functions that are the type y equals a times b to the exponent x. And a and b can be almost any number. Almost any number. The only thing is that a can't be 0, and B can't be 0 or 1. Other than that, everything else is fair game. So what we want to do is we want to take a look at what the graph looks like if B is larger than 1. So that is what we would call the base. If that's bigger than 1 and A has to be positive, then we get a graph that looks like this. Basically, the importance is it starts really low, it increases, and it goes, and it goes, and it gets really big. Okay? Now, if that b value is between 0 and 1, then the graph is decreasing, and what happens is the graph gets flipped on the y-axis and it decreases. It starts really high, gets lower, gets lower, gets lower, decreases towards, but not on to 0. Okay? It never touches 0. So, let's look at some properties of exponential graphs. If we look at an increasing one, which is this friend right here, that's an increasing one. It's an increasing one because it's going up as we go from left to right. Any function is increasing if the values are going up from left to right. Here are some things that we see. It never touches the x-axis, never ever. The y-intercept is whatever the a value is. And I did mention that yesterday. And it increases from left to right or decreases from left to right. But if it's an increasing one, then it does this. The domain is all real values, and the range is anything bigger than 0, not equal to 0. Okay? And if we have a decreasing one, all this is also true, except it's decreasing. If we take a look at these two graphs over here in the bottom right-hand side of the screen, the red one grows quicker and is steeper, and the difference between the red graph and the blue graph is the graph that is to the left has a larger b value. B represents how quickly the graph is growing. The larger the b value, the quicker it grows. Okay? All right? Okay. So, let's take a look at some examples. We're going to start with considering the function y equals 4 times 1.5 to the exponent x. So just for clarity, 4 is your a value and 1.5 is your b value. And what we want to do is we want to figure out the x-intercepts, the y-intercept, the end behavior, the domain, the range, whether or not the graph is increasing or decreasing, and then we want to make a table of values. Now, one of the cool things about this question is you can use Desmos or your calculator. It really doesn't matter. One of the cool things about this question is we can answer all of those questions without actually graphing it. If you just remember some of the discussions we've already had. So help me out here. What would the x-intercept? Where would the x-intercept be? None. There's no x-intercepts. What would the y-intercept be? We can either say 4, or we can either say it's 4, or we can write down the whole point and say it's 0, 4. Either way is fine. Okay? The y-intercept is 4, but if you want to write it down as a whole point, it's 0, 4. The end behavior, well, that's easy because all of these go from which quadrant to which quadrant? 2 to 1. What's the domain? Negative infinity to infinity. Again, we don't even have to graph it to know that. What's the range? Right? What kind of bracket on the 0? Round or square? Round, because it can't be 0. Is the function increasing or decreasing? Now this one, we have to actually think about a little bit, but we don't have to graph it. Is it increasing or decreasing? What's that? Why? This right here is bigger than 1, so it is increasing. Now it does say make a table and graph the function. So again, we looked at how to make a table with a graphing calculator. We looked at how to make a table with using Desmos. I'm going to demo it with the graphing calculator. So we're going to go to the graphing calculator, going to go to your y equals, clear out any equations that might be in there, similar for Desmos. Then it's going to be 4 bracket 1.5 to the exponent x. So that's exponent x. And then we should set up a table that we're willing to live with. Now, really, a couple values into the negative is a good idea. So I would say go second table set. It says it's starting at -3 and going up by 1. That's awesome. So just hitting second table then and letting these values be our guide. So we're not going to just copy these values, but just to make things a wee bit easier on my not so wonderful memory, we're just going to take this. I'm going to just paste it here, and we can go ahead and make a table of values from this. And this won't stay here forever. It's just going to be here as a guide. So if we went from -3 to 3, or even -2 to 4, that would be fine. So I'm just going to make some, okay? -3 would be 1.19 if we write it to 2 decimal places. -2 would be 1.78. -1 would be 2.67. That's going to be tough to write in that space, but I'll do my best. 0 gives us 4. 1 gives us 6. 2 gives us 9. And 3 gives us 13.5. And I don't have much more room, so I think I'm going to stop right there, and I'll go ahead and just flip that up there because I don't need that anymore. There's our table of values. So hey, listen, the way you've done math before this class, as far as finding a table of values goes, I even have my grade 9s do a table of values. What you have to do is you have to jam away and do a bunch of repetitive calculations. Well, we don't have to do that when we have the technology. We can have the technology tell us all the values, and all we need to do are take those values and make an appropriate scale on our graph and plot the points and see what we get. So x, as we go from -3 to 3, hey, listen, I'm actually willing to do this: -1, -2, -3, -4, -5, 1, 5. For values, we go up to a maximum of 13.5. There's 15 squares. I might as well just make each one worth 1. So that means that this would be 5, 10, 15. Okay? Could you use a different scale than I used? Yep. Would you be wrong? Not necessarily, as long as you use the appropriate numbers and as long as we can fit all those values on our graph. So -3 and 1, well, that would be like right about here. -2 and 1.78. -1 and 2.67. 0 and 4. 1 and 6. 2 and 9. And 3 and 13 and a half. So you should see something like that on your page once you've plotted each of those points. Okay? And then once you have that, what you need to do is you need to draw a smooth curve connecting those points. So I sometimes struggle with this. I don't know where to start, but what we could do is something like this. There we go. And as bad of a artist as I am, I gotta say I'm pretty happy with how that turned out. Okay? So what would make a bad graph? If your graph touches the x-axis, that's bad. Don't do that. If it crosses the x-axis, that's bad. Don't do that. You want to draw it smoothly between the points, and at the far right of the graph, you want the graph continuing in the upward direction as it is. So if your graph looks like that in general, you're good. Okay? Any questions about drawing graph? Okay. So the properties of an exponential function are pretty straightforward. Keep those in mind because they are important to know. A couple more examples. Here's the first one. Same idea. This time we've got 180 times 1/3 to the exponent x. We want to know stuff like the x-intercept, the y-intercept, etc., etc. Let's figure all this out. Hey, what's the x-intercept? None. That's right. Don't put 0, because that implies that 0 is your x-intercept. I don't have to have it back this second, guys. You can give it back to me a little bit later. It's all good. If our A value was negative, then the graph would be flipped upside down. And in situations like that, it would be 3 to 4. But we're not really going to look at situations like that very often, or maybe even at all. So I wouldn't say we'd even need to worry about those things. What's the y-intercept here? What's the y-intercept? 180. What's the end behavior? Quadrant 2 to 1. What's the domain? Negative infinity to infinity. That's right. What's the range? Round bracket on the 0. Is the function increasing or decreasing? What's that? Decreasing, correct. B is between 0 and 1. So this one's decreasing. So again, what we want to do is we want to make a table of values. Now, hey, listen, I'm all for using the calculator to do all your work, but I'm also for a little bit of thinking when we can think and come up with nice values. So listen, if we were to make a table of values here, ooh, I don't like that because I want more values to be possible. There we go. Okay, here we go. I'm going to go -3, -2, -1, 0, 1, 2, 3, 4. Like, what do you mean? Julie asked a wonderful question. She asked, are we going to be doing something with Desmos orthographing calculator to connect the dots on its own to make an equation? And Julie, today you're the grand prize winner, because what we'll be doing when we study, that's what we're gearing towards. That's what we're gearing towards. Once we know these properties, once we understand what exponential functions look like and the properties that they have, that's exactly where we're going in the next day or two. So absolutely, we're heading there. Yeah, we are heading there. And we're going to do the same thing with logarithmic functions. We're going to learn all about them, and then we're going to learn how to figure out equations to model logarithmic situations. And last but not least, the final unit that we do on sinusoidal functions, that's trigonometry. We're going to actually be able to feed data into the graphing calculator or into Desmos and come up with a trigonometric equation. But actually, that's the interesting piece, is Desmos does a lousy job at calculating sinusoidal equations. So when we get to that last unit, Desmos will be helpful at times, but it will not be helpful when coming up with an equation. When we come up with an equation for the last unit, the graphing calculator is going to be the tool of choice. And actually, a couple weeks ago when I got that phone call right at the end of the school day, it was a teacher from Swan River, and he was asking me if I knew a way around that with Desmos, and there's no way around it. It just does a lousy job with that particular thing. Does a great job with everything else, but just not with that. So listen, when x is 0, y will be 180. Okay? Because anything to the 0 is 1. 180 times 1 is 180. Then as we move to the right, what we have to do is we have to take a third of the value. So what's a third of 180? If I have $180 and I want to divide it among the 3 of you students, how much is everyone getting? A third, not 2/3. Yes, everyone's getting 60. Okay? Now, if I want to take 60 and divide it 3 ways, how much is everyone getting? 20 goes here. Now, this gets a little trickier, I'll admit. What's a third of 20? What's a third of 20? Well, you could do it on your calculator if you want to, but a third of 20 is going to be 6.67. 6 and 2/3, 20/3. And a third of that is going to be 2.22. Now in the negatives here, we have to keep going in the reversed way. Instead of dividing 180 by 3 to get 60, what's 180 times 3? 540. So we have 540 here. And if we multiply that by 3, we get 1620. And if we multiply that by 3, we're going to get 4860 right here. So you can see that the numbers get ridiculously big as we move to the left. Now, I don't know that we need to go like super high when we take a look at these. As a matter of fact, I don't think we need to go super high at all. So here's what I think we should do. As we go for our x's and our y's, if we pick just 1, 2, 3, 4, 5, -1, -2, -3, -4, and -5. For our y's, I don't care about the really big numbers, honestly. We could go up by 20s. I was thinking go up by 40s, but I wouldn't be opposed to 20s. I like 40s though, because at least captures one of these. So if we go up by 40s, then that would be 200 here, 400 here, and 600 here. Tomato, tomato, if you want to go up by 20s, that's okay. I just want to get one of those negative numbers in. So really all we're looking at is -1 onwards for values, because nothing else is under 600. So -1 and 540, that's going to be, every block will be 40. So that's going to be 560, 520. So 540 is right here. -1 and 540 is going to live right there. Zero and 180 is going to live right here. 1 and 60 lives here. 2 and 20 lives here. And you can see very quickly, 3 and 6.67 is really close to nothing. And then we get really close to nothing. So we do have to be careful when we draw this because we don't want touching the x-axis. So we're going to go ahead and try to trace this through as best as we can. And I'm not thrilled with what I just drew, so I'm going to get a reboot. I'm going to do it again. I'm not thrilled with that either. Oh boy. Let's try this again. There we go. Took my time, and I'm a little bit happier with that. Not thrilled with it, but I can live with it. Okay? So there's a graph of 180 times 1/3 to the exponent x. Again, your curve should be touching these values. These are exact values that are on the function. When we do the regression stuff later, they won't be. And sometimes the curve won't touch the values. But if we're graphing a function, the function should pass through each of your dots. If it doesn't, it means you didn't do it right. So make sure your curves pass through your values, except for when we do regression. When we do regression, you might have values that are outside, and that's perfectly fine. Now, the last thing that we're going to do here today is we're going to take a look at 4 different graphs, and we're going to try and match the graphs to 4 different equations. Now, I think this should be pretty straightforward, so let's see what we can figure out. So I want you to look at 20 times 1/2 x to 1/2 to the power x, which is f of x. Which one of those graphs, A, B, C, or D, is f of x? F of x. Which one of those graphs is f of x? What's that, Malcolm? C or B? C or B? C or B? Yes. Let me ask you this. What's the y-intercept? What's the y-intercept? 20. So what graph is it? B. It is B. G of x. Which graph is G of x? Is it A or is it D? It is D. Because the y-intercept is 2. That's not 2. That's 5. It's a trick though. H of x is what graph? C, because it's the only other decreasing graph. And J of x is? I hope not. A. Because the y-intercept is 5. Okay? What else do I want to say? I guess I want to say this. If I look at this graph right here, graph A, you see here it's 5. And when x is 1, it goes up to 10. When x is 2, it goes up to 20. So if we take a look at that for a second here, it goes from 5 to 10. It goes from 10 to 20. So if it goes from 5 to 10 and 10 to 20, what do we multiply 5 by to give us 10? What do we multiply 10 by to give us 20? So that tells us that the base must be 2. What's the base here? Not a coincidence. Okay? That 2 is why everything gets multiplied by 2 here. And if we go to the next one, we go from 20 to 40. What do we multiply 20 by to get 40? So the next value would be, and then, and so on, and so on, and so on, and so on. Okay? All right. Your homework is on pages, what's that? Your homework is on pages 448 to 453, numbers 1 to 20.